When you type a question into an AI model, the response is near instant. In the milliseconds after you hit enter, a vast system expands to converse with you, answering complex questions with the fluidity of a human on the other side of the screen. This capability rests on a paradox. A computer does not actually know what a word is. It possesses no dictionary, no eyes to see a sunset, no lived experiences to draw from. At its core, a computer only possesses the ability to perform mathematical operations. Because a machine cannot process the letters in a word like apple or existentialism, we have to bridge that gap. Before an AI can even begin to read your prompt, every single piece of human language must be translated into a purely numerical format. Instead of a text definition, a word unfurls into a very long list of numbers. Think of these numbers as specific coordinates. Just like longitude and latitude tell you exactly where a city sits on a physical globe, these numerical coordinates give every concept a specific location on a vast mathematical map. To teach a machine to speak our language, engineers first had to figure out how to transform human meaning into pure mathematics. This chart shows a simple two-dimensional map of meaning, plotting words based on two traits: size and fluffiness. If we look at the data points, words like cat and dog cluster closely together in the upper right. Meanwhile, a word like whale is plotted far away, over in the massive, non-fluffy corner. Words that share traits sit near each other, while unrelated concepts are pushed apart. Of course, human language involves far more than two traits. To capture every nuance of thought, gender, emotion, grammar, tone, the map explodes outward. We add a third axis, a fourth, a fifth, all the way up to over 12,000 invisible axes. It becomes a hyperdimensional web that organizes the entire human vocabulary. This specific list of coordinates that defines a word's permanent location in this conceptual galaxy is called a vector embedding. A vector embedding is a high-dimensional array of numbers that a machine learning model uses to represent the semantic meaning of a piece of text. Because these coordinates are purely numerical, we can perform actual algebra on language. If you start at the spatial coordinates for king, subtract the vector for man, and add the vector for woman, the resulting math lands you on the note for queen. Semantics and logic are no longer abstract ideas in the human mind. They are measurable geometric distances that a calculator can navigate. But a static coordinate system has a glaring flaw. Think about the word bank. If I mention a riverbank or a bank account, those are completely different concepts. A single fixed location on our map is useless if the word has multiple, unrelated meanings depending on the sentence it sits in. To solve this, the model needs a way to look at the surrounding words to deduce which version of the definition is currently in play. It accomplishes this using a mechanism called self-attention. Self-attention is a mathematical process within a transformer model that allows a word to actively scan its neighboring tokens to gather contextual clues. When a sentence is processed, a target word does not sit in isolation. Instead, glowing lines shoot out to connect with the surrounding nodes. The model measures the relational weights between them, calculating how relevant the target word is to the other words present in the sequence. The mathematical result of this attention acts like gravity. If the word bank scans its neighbors and finds words like river and fish, those surrounding words end up physically dragging the target word's coordinates away from the finance area of the map, pulling it into the nature cluster. Inside a language model, meaning is never static. It is dynamically calculated based on the gravitational pull of every surrounding word. Now that we know how words are mapped and given context, we can look at how the AI actually uses this map to write sentences. The model evaluates the sequence of coordinates it has processed so far. It traces the trajectory of that path through the dense web to determine the exact location of the most logical next step. Once it plots that ideal next step, the model looks at every single word in its vocabulary. It generates a raw numerical score for each one, based on how physically close it sits to that predicted endpoint. This chart shows a probability distribution. A probability distribution is a mathematical function that converts those raw proximity scores into percentages, allowing the model to rank the most likely next words. The closer a word is to the target coordinate, the higher its percentage bar shoots up. Generating text is a high-speed, multidimensional operation, a continuous statistical prediction of the closest next coordinate. If the AI always chose the absolute highest probability word every single time, its writing would become highly repetitive and predictable. It would always take the most obvious path. To prevent this, engineers use a mathematical setting called temperature. Temperature is a hyperparameter that scales the model's raw scores before they become probabilities, which flattens the distribution curve. This makes the alternative choices visually competitive, allowing the AI to occasionally pick words that are slightly further away on the map. This forced deviation from the most obvious path is what gives the text a sense of unpredictability. It's what humans perceive as creativity or personality in the AI's writing. The machine does not understand our language, our emotions, or our reality. What looks like understanding is simply an illusion. It is the result of billions of rapid calculations performed across a massive geometric map of human thought.